Okay, welcome back. This is now 14.2, and we want to now go to 3 dimensions with our double integrals and use them to determine volume. Okay, and we've kind of touched on this just a little bit with the idea of a triple integral in the previous video, but the idea is that well, let's dive in here with the Riemann sum. Okay, and what are we trying to do? We're trying to find the volume between the xy plane and some surface, or you could generalize that to anything you want. Trying to find volume between two surfaces, just in general. But in the beginning, what they're going to do is have you try to find the volume underneath the surface over top of some region, usually in the xy plane. Right? So here are our axes. So your x-axis, your y-axis, your z-axis. And then we'll have some surface over top the xy plane. We'll just keep it in this one octant. Okay? So here's my sort of bubble surface. Something like that. Okay. And I want to find the volume inside this bubble surface over top of this region, this semicircular or type region in the plane, right? So what I'm going to do is chop up all this whole region, this xy plane, into a bunch of rectangles. Okay? And it's similar to what we did in Calc 1, where we chopped up the number line into a bunch of subintervals. Okay, so here we go. The same sort of graph, x, y, and z. In particular, I want to kind of zoom in on this region in the xy plane. Let's see if I can reproduce it over here. And I'm going to chop it up into a bunch of rectangles. And then, so corresponds to chopping up this region into a bunch of rectangles. Each one of these rectangles will have an area associated with it. So you can say, all right, this particular rectangle here has an area change in a sub I, which will just be kind of a width in the x direction times a width in the y direction. Okay. And we're going to say overall there's this norm that we're dealing with. This norm value, which is going to be the control on how big or how small these rectangles are. And with the Riemann sum, we had norms as well, and the norm would be the length of the largest interval that we are integrating over. Here, the norm represents the length of the longest diagonal on any of these squares. Okay? Length of longest diagonal. Okay, so the deal is to get your integral, the smoothing process, where before we would take the limit as the number of rectangles went to 0, or if you'd rather take the limit as the length of the intervals you're integrating over went to 0. Sorry, the number of rectangles goes to infinity, right? So the limit is the limit as the number of rectangles went to infinity, or as the length of the subintervals that you're integrating over went to 0. So this is we'll let this thing go to 0 in our limit, and that will give us the sort of sum that we're after. So what is the Riemann man sort of doing in this problem? Well, he's going through all these rectangles, and he's figuring out a volume sort of associated with each rectangle. So for instance, this particular rectangle here would have a volume associated with it. So if I went over to this graph here, maybe it would go up to about right here, and it would touch the surface there. Right. So on the inside, the Riemann man would go to this guy here and figure out the volume of that particular rectangular solid, V sub I, which would basically be the surface being evaluated at a particular x sub I comma y sub I times this area on the bottom, okay, times change in a sub I. And then the Riemann man would be adding up all of these things to get an approximation for the volume, right? So this V sub I, and then they would be taking the limit as the norm, the length of the longest diagonal went to 0. So you would have basically this region underneath the surface populated by all these mini rectangular solids, and that would give you the volume. Okay, so this would be the limit as the norm went to 0 of the sum of the V sub i's. And at the end of the day, we'll call that the double integral over the region R. Okay, so this region here that I drew in the xy plane is our R region, okay, of f of x comma y dA. And they'll call that the double integral of f over R. Okay, so one thing to note here at this point, we've not really connected it to the iterated integral. This is just kind of a symbolic form for what we've accomplished with the Riemann sum. Okay. In the beginning, they'll take you through some sort of numerical analysis type problems where you'll be forced to go through like a primordial or an early hominid version of the Riemann man, and actually just get the volume of the rectangular solids, and then make an approximation of the volume underneath this surface. Okay, so we want to try one of those, and I think there's one in the My Open Math. There's a video associated with that problem in My Open Math, so you probably want to watch that video as well, but I don't know. So anyways, in this problem we want to approximate using 8 squares and find the sum basically of f of x sub I comma y sub I times change in a sub I, where we'll have the x sub I, y sub i's be the center of the squares. Okay? Okay, so this is problem 1. It's a double integral from 0 to 2 and then 0 to 4 of x plus y dy dx. Okay, so the surface is plane, and the region we're integrating over is going to be, it looks like it's a rectangle. Okay, so let's go ahead and draw that rectangle. This means go y equals 0 to 2. So y equals the line, y equals 0 is the x-axis. And then y equals 2 is a horizontal line at 2. And then the x-axis, I'm going from 0 to 4. Okay, so we get this rectangular region. to integrate over. Okay. Then I'm going to section it up, okay, into 8 squares. So 1, 2, 3, 4, 5, 6, 7, 8. And then I need to use the midpoints of those squares in order to approximate the volume of the surface between, this region and the surface. So not approximating the volume of the surface, obviously. It's approximating the volume underneath the surface, but over top this region. And the surface is some, what did I say it already? It's a plane of some sort. Okay, so I need all these points in order to figure this out. Right? So what the heck are these points? So this point here is 0.5, 0.5. Then this point, 0.5, and then 1.5, etc., right? 1.5, 1.5, 1.5, 0.5, and then 1.5, comma 1.5. That's all of this stuff. And then these guys, so 2.5, 0.5, and then 2.5, 1.5, and then 3.5, 0.5, and then 3.5, comma 1.5. Okay. Okay, and then I'm just creating this sum from, whatever I equals 0 or I equals 1 to 8, if you want, of f of these coordinates. Okay, so f of x sub I, comma y sub I, times change in a sub I. In particular, then, the function, this surface is just this x plus y thing. Okay. So I have the sum of x sub I plus y sub I from I equals 1 to 8. And then the change in a sub I, the area of any of these rectangles is just 1. Right? So length is 1, height is 1. 1 times 1 is 1. Okay, so all am I doing, what am I doing, overall? It's just adding x plus y plus x plus y plus x plus y plus x plus y, right? So this will equal 0.5 plus 0.5 for the first one, which is 1, plus 0.5 plus 1.5, which is 2, plus 1.5 plus 0.5, which of course is 2, plus 1.5 plus 1.5, plus 2.5 plus 0.5, plus 2.5 plus 1.5, plus 3.5 plus 0.5, plus 3.5 plus 1.5, 4, 5, 10, 18, 19, 20, 21, 22, 23, 24 is what we're hoping is the approximate value. Okay. Okay. So let's now move to evaluation of these things and how they work. And it's pretty simple so long as the surfaces you're dealing with are oriented in a nice, simple kind of way. So if you have, like, you could tell the orientation. So like before with the Running Man, you could always tell where the top curve and the bottom curve were. Here it's going to be, you can always tell where the bottom surface and the top surface are. Okay? That's kind of what we need for this to work out. With regards to the book, they kind of walk you through what's going on here with regards to these iterated integrals. And I'll kind of go with their exploration. In particular, let's look at number 19. Z is y over 2, the surface y over 2, which is a plane that's cutting through the YZ plane in a straight line, y over 2. And then we want to just consider the region over top of this rectangle where x is restricted to 0 to 4 and y is restricted 0 to 2. Okay, so what the book does is to say what the integral is doing is finding sort of cross sections and then adding it up. So when I always said curve the curve and then point to point, um, we're going to have on top of that kind of a function on the inside. So when we go curve the curve, we're going to be thinking of adding up the area of a bunch of cross sections. Okay, so let me try to make that clear. The way the iterated integral work will be to first find the area of the cross section. Okay. So, and the picture as it stands, we're in the XYZ plane again. Hopefully I gave myself enough room to pull this off. This is X, this is Y, this is Z. So in the XY plane, we have basically a rectangle. X is 0 to 4, Y is 0 to 2. Okay, so we have this region that we're integrating over top of. And then in the YZ plane, we have this projection, Y over 2. So the slope in the Z direction go up 1 over 2. So up 1 I'll put right here, and then over 2 will give me this point. So that'll be the curve in the YZ plane. Okay, so we have this triangle. And what we're doing then, this plane is pretty simple. It's, it's going to be this triangular sort of solid. So I'm integrating firstly to find the area of a cross section of this triangular solid, and then what the Riemann man is going to be kind of doing is running along one of the axes, adding up the area of these cross sections. So a cross section in particular would be something like this, right? And we would need to know the area of that. In this case, it's not a variable area, right? So if I'm right here on the x-axis, it's going to have the same area as if I was right here. So to find the area of that cross section, you can kind of just look at the YZ plane and find the area from 0 to 2 underneath this curve y equals 2. So again, up 1 over 2 based off the slope of this as a line in the YZ plane. So you can do that with geometry, but you can also do it with an integral. We're going on in this orientation. Okay. So the Riemann man will be going from 0 to 2 on the y-axis, and we're integrating underneath the curve y over 2. Okay. So that will give me the area of this particular triangle, and then we're going to integrate again, but we want to integrate these areas from 0 to 4, and that will tell us the volume. Okay? So basically, you're slicing it up into a bunch of areas and then adding up all those little areas, and that gives you the overall volume. And it's the same thing what you did in Calc 1 to find the area of a region. You sliced it up into a bunch of little lines, I guess, and then added up all the little lines. I don't know. Anyways, let's take a look at this. So y squared over 4, I guess, and then I'm integrating from 0 to 2. That will be 4 over 4, which is 1, minus 0 over 4, which is 0. Okay, so the area of the cross section is just 1. And then I want to basically sum that up from 0 to 4. So I can do that with another integral, right? So I can say, okay, step 2, sum up the cross sections. So I do an integral from 0 to 4 of these areas on the x-axis. And there we go, sorry about that. I need to add up the area of these little triangles from 0 to 4. And so what do I get there? I get x evaluated from 0 to 4, and that will equal 4. Okay, so overall, what did I do? If you put this together, basically you're taking this thing and you're kind of inputting it into here, right? And that's the double integral. So this thing is the same as integrating from 0 to 4 and integrating 0 to 2 of y over 2 dy dx. Sorry about that. Okay. So you can use a double integral to figure out volumes. The one thing you have to worry about is just making sure that the thing is, the surfaces you're working with are kind of simple and they're not intersecting in weird ways, which would force you to maybe say, okay, from here to here, from this region to this region, I have this surface and this surface for my bottom and top surfaces, and then from this region to this region, I have these other surfaces. And it does come up every once in a while, but usually everything's simple enough that you can apply what's called Farini's theorem, which is just use an iterated integral to find the volume. Okay, the Farini's theorem's in the book. I'm not going to go into it. Okay. So let's try working with some of these. And again, the game is to set up the integral for both orders of integration. So this is problem 11. I'm integrating to find the volume underneath the surface xy over top of the region R. And the region R is given in the book as a rectangle. Okay, so 1, 2, 3, 1, 2, 3, 4, 5. This point here is 3, 5. Okay. We want to set up for the integral for both orders of integration. So it'll be xy, and then we want to do dy dx, and then we want to set it up for xy dx dy. So in dy dx order, that's this orientation. Okay. And then the other guy, dx dy, is going to be this other orientation. Okay. So y equals what to y equals what? Y equals 0 to y equals 3. And then the running man is going from 0 to 5. Y equals 0 to y equals 5. And then the running man is going from 0 to 3. And the other orientation, I'm going in now this direction. The curves x equals 0 to x equals 3, and then the Riemann man is going from 0 to 5. So x equals 0 to x equals 3, and then the Riemann man is going from y equals 0 to y equals 5. Okay. Whoops. Try another. Number 15. I got the double integral over this region R of negative 2y dA. Okay. The region, again, is given in the book. This region is a little more complicated. We want to integrate over the region enclosed by the curves 4 minus x squared, y equals 4 minus x. In order to pull off both orientations, I'm going to need these solved in terms of y. So I'm just going to get that out of the way, right? So I move the x squared over and then take the square root on both sides, get x equals the square root of 4 minus y. And then over here, x equals y minus 4. Okay. Let's look at the graph of this region. Okay, so this guy is a parabola flipped upside down and moved up 4. X-intercepts at negative 2 and 2. Okay, and then this guy is just a line with slope negative 1, x-intercept at 4. 1, 2, 3, 4. And then it goes something like that. I don't know where it intersects, so I'll have to set these equal to each other and find out. Okay, so 4 minus x squared equals 4 minus x. And I'll have x squared minus x is 0, so x times x minus 1 is 0. So x is 0 and x is 1. Okay, so it should be a little bit over here more, and the location of these points probably be helpful to know. This is at 0, 4, and this will be at 1. And if you plug 1 into this equation, 4 minus 1 is 3. Okay, so for the traditional orientation, I'm going from y equals 4 minus x to this curve. The bottom curve is 4 minus, so let me write it up. Negative 2y, and then I got what, dy dx. Okay, so y equals one curve, the bottom curve to the top curve. So the bottom curve is 4 minus x. And then the top curve is the parabola. Okay. So the top curve is 4 minus x squared. And then the Riemann man is running from x equals 0 to x equals 1. Okay, 0 to 1. Okay, and then for the other order, the other orientation, the Riemann man now is running like this. So the bottom curve, we're going from x equals something to x equals something, right? So the bottom curve is the line. So x equals square root 4 minus y. Oh, sorry, y minus 4. And then the top portion is the parabola, and this is the positive root part. If we had plus or minus, the negative part would be this part. So I don't need that part. I just need this part for the top. Okay, so that would be square root of 4 minus y. And then the Riemann man is running from the y coordinate 3 to the y coordinate 4. Okay, he's going from 3 to 4. And then you would have to integrate. So I'm going to skip the integral part. I'm hoping you can do that yourself. Okay, let's look at number 17. This one's a little more complicated. Double integral of x dA over this region R, again, is given in the book. Excuse me. R is a region enclosed by y equals the square root of 25 minus x squared, which is the upper hemisphere of a circle. It's radius 5. Line 3x minus 4y is 0. And then y equals 0. And we want to restrict ourselves to the first quadrant. Okay. So let's first get this region, I guess, drawn out. So this thing is a circle with radius 5. This thing right here, you could write it in terms of y or terms of x. It'll be 4y equals 3x. In other words, y equals 3/4 x. Okay? Or you can write it as x equals 4/3 y. Okay? So that means intercept at 0, and then you go up 3 over 4, right? So 1, 2, 3, 1, 2, 3, 4, somewhere in there, somewhere. I still have to kind of figure out where it's hitting. Then y equals 0 is the x-axis. So the region enclosed is this region here. For this orientation to pan out, notice it's not all that simple, right? There's 2 regions to deal with. And in particular, then the Riemann man is going over through to here with this guy on the top and this guy on the bottom. And then afterwards, it's the circle that's on the top and then the bottom. Okay? So in this case, it's probably easier to do the other orientation. Otherwise, you're going to have 2 integrals to deal with. Okay? But we want to do both orders of integration, so let's sort of get at it. So for the first order, I'm doing x, and I want to have it in the dy dx order first. So curve the curve, and I have to put it in the two integrals. So I'm going to have to go plus another x dy dx. So the first integral, the Riemann man, is going to go from 0 to this point, and then the second integral, he'll go from this point to this. I need to figure out this point, by the way. So you just set the two equations that are intersecting equal to each other. So you take this and set it equal to that, or this and set it equal to that. So I'll have square root of 25 minus x squared, and set that equal to 3/4 x. Square both sides, I get 25 minus x squared equals 9/16 x squared. Okay. You can add this over to the other side. 16/16 plus 9/16 is 25/16. X squared equals 25. Multiply both sides by 16 over 25 and get x squared equals 16. So x is plus or minus 4. But in particular, we just want the positive one. And then y, if you plug y back into your y equals 3/4 x formula, y equals 3/4 times 4 is 3. Okay, so this point here is located at 4, 3. So the Riemann man is first going from 0 to 4, and then from 4 to whatever this point is, and we know because it has radius 5, that must be the point 5, 0. Okay. So here will be 5. Okay, I need to work the other order of integration as, oh sorry, I didn't do the integral, sorry. So in the first case, it goes from y equals 0, which is the x-axis, to y equals this line, which is 3/4 x. And then in the next region, it's going from y equals 0 to this circle, okay, this hemisphere. So y equals 0 to this y equals square root 25 minus x squared. Okay, what a nightmare, right? This is not the integral you want to be doing. You want the other orientation. Hopefully that'll be a little nicer. So we want to do this job here. And it's nicer, I think, right? So the bottom curve is always going to be this line, and the top curve is always going to be this. So yeah, it'll just be one integral in the other orientation. Should let me quarantine all that junk. I got a double integral of x dx dy. Okay. And in this orientation, the Riemann man is going to be going from 0 to 3, right? So I just use the y coordinates 0 to 3 for the y. And then I need equations x equals this line to x equals this line, the bottom curve and the top curve. So the bottom curve, I already sort of found x is 4/3 y. And then the top curve, I didn't really solve for that, but it's just taking this and put it in terms of y, right? So square both sides, move the x over, x squared over, move the y squared over, and you'll end up with x equaling the square root of 25 minus y squared. And of course, that hemisphere is the hemisphere that goes like that. Okay? But we only want to go from here to here. And the Riemann man is taking care of that problem. So I just need the equation for the top curve in this little region here, basically. And I found that to be this guy. It doesn't look any nicer or any prettier, but this one is a little bit easier to work with. Okay. Let's now look at some more complicated regions, some more complicated type problems. In these types of problems, the book gives you a nice three-dimensional graph. And so problem 23. Okay. I'll try to draw it. Okay. So we have our x-axis or y-axis or z-axis. In the xy region, we have a box. Well, we're going to be integrating over a triangle, but you can think of a box going one up here, one over here. So in the xy plane, it's actually y equals x. And I kind of need some help there. Y equals x to right here. And then y equals 1 is this guy right here. Okay, so in the xy plane, we can kind of draw that out. And that may help later when we're saying, we're going from this curve to this curve. So I have the line y equals x, and then the curve, or the horizontal line y equals 1 right there. So this point is 1, 1. Okay, that's this region here is this region here. Okay, over top of that region, we have this object, or the surface rather, sorry. So going from here to kind of right here. And then it's coming down onto that point. Like that. Okay. So the surface is this thing. Okay. And we're integrating that over top of that triangle region. And they want you to set up the integral for both orders. They tell you information. This surface is given by the equation z equals 1 minus xy. This curve, this line, is just y equals 1. And then this line here is y equals x, okay, which of course is just over here as well. Okay, so we need to set up our integrals for both orders. So the first integral, I'll do it in the kind of traditional method. So inside the integral, you're putting the surface, so 1 minus xy. And then first we're going to do dy dx. So I want to go from y equals this curve. So this is a traditional orientation. My running man is oriented like that. So I'm going from this curve to this curve here. So y equals x to y equals 1. And the Riemann man is running from 0 to 1. Okay, so that's our first integral. And then the second integral, the insides are the same, so 1 minus xy. But now we want dx dy. Okay, so the Riemann man is now oriented in this direction. Okay. And in this direction, the Riemann man is running from 0 to 1. The curves are going from x equals 0 to x equals y, right? And that will give us the two integrals. Okay, regions bounded now by two surfaces. Getting more complicated here. You could think of these sort of like the three-dimensional version of finding the area between two curves. So for the inside of your integral, you're thinking difference, of course. So before, the area between two curves, your integral would basically be f of x minus g of x, right? The top curve minus the bottom curve. Now, to find the volume between two surfaces, assuming the surfaces aren't like doing some crazy intersection business, you're going to be taking the difference of the two surfaces. So you'll have some f of x comma y minus g of x comma y. And then later we'll see we can convert this into a triple integral, right? Because we could just make this portion another integral from surface to bottom surface to top surface. Okay, so let's look at, this used to be example 5, they probably changed it, but we want to find the volume of the solid region bounded above. So the top kind of surface is z equals 1 minus x squared minus y squared, which is an elliptic paraboloid. And then the bottom surface is going to be z equals 1 minus y, which is just a really simple plane. Okay. To kind of find the region that we're integrating with respect to, with the region that we're integrating over top of, this R region, what I'm going to do is project the intersection of these two surfaces into the xy plane, okay? So the intersection of these two surfaces is a cylinder, okay? So if we took these and set them equal to each other, 1 minus x squared minus y squared equals 1 minus y, I can sort of solve for the intersection. And it's not a traditional intersection, right? It's going to be a curve with z that's absent. So if you let z vary, then what you get is a cylinder. Right? So anyways, if I move the x's over, if I move the x squared over, or move the y squared over, the ones will cancel, and then I'll have a minus y equals 0. You can complete the square, x squared plus y squared minus y. To complete the square, it's always b over 2 squared, where b in this case is from this term. It's negative 1 over 2. So if I square that, I'll get 1/4, and they add it to the other side to keep it in balance. Factor, so I have x squared plus y minus 1/2 squared equals 1/4. And certainly that if we were in 2 dimensions, this is the equation of a plane of a circle. And that's where z is basically 0. So in 3 dimensions, this is a cylinder where z varies over the real numbers. When z is 0, that will tell us kind of the region in the xy plane that we want to integrate sort of over. Okay, it's the restriction. So what is this thing in the xy plane? It'll be a circle where the center is at 1/2, so 0, 1/2, and then, sorry, the center is at, yeah, 1/2, and then it goes up to 1, so it'll be a circle radius 1/2. Yeah, it'll look like that. Okay, we want to then basically integrate over that region, and that tells us kind of how to set up the limits on our integrals. The inner part we don't have to worry too much about. It'll just be the two surfaces. The hard part are the limits on the integrals. So it corresponds to the process that we would have used over here, right? So in Calc 1, we would have, or Calc 2, we would have just set these equations equal to each other to figure out the limits on the integral. Now we're setting the surfaces equal to each other, but we don't get a nice interval in the number lines, on the number line on the x-axis, right? And now instead we're getting basically a region in the xy plane that we have to work with. Okay, so I hope that makes somewhat sense. It's not entirely clear in my head either, but the way I'm approaching it will get the job done. Okay. So here we go. What am I doing? Okay, so I have to set up my integrals. So I'll have the integral of the difference of the two surfaces. So the first surface on top, 1 minus x squared minus y squared, and then minus the surface on the bottom, which is 1 minus y. And then I go, I'm going to do the sort of traditional ordering dy dx. Okay? So my Riemann man is oriented like this and going over that region. So recall this thing is actually two curves in this orientation. You have the negative portion of it, and then there's the positive portion. Okay? This portion here, the upper hemisphere is the positive portion. So my Riemann man, it'll go y equals this curve to y equals this curve, and then I'm going to have to run on the x-axis from this point to this point. So that would be the negative 1/2 to positive 1/2. So at least I can kind of get rid of that issue, right? So in the x orientation, I'm going from negative 1/2 to positive 1/2 on the outside part of the integral. On the inside, then, y equals this bottom hemisphere to y equals the top hemisphere. And to get that, I'm going to have to solve this thing for y, right? So a little bit of work there, but no big deal. Y minus 1/2 squared equals 1/4 minus x squared. Do square root on both sides. So I get y minus 1/2 equals plus or minus square root of 1/4 minus x squared. And then add the 1/2 to the other side. So y equals 1/2 plus or minus square root 1/4 minus x squared. And the bottom curve, the pinkish curve, is the negative part, and the green curve is the positive part. So I'm going from the bottom curve, and this isn't going to be pretty, but here it is, 1/2 minus square root of 1/4 minus x squared to the top curve, which now is just the 1/2 plus, right? And then you'll have some fun integrating that thing. But that kind of gets the job done. And all right. That's pretty much all I want to talk about in this section. There are average values in there, which is, if you know the Calc 1 version, you know kind of the Calc 2 version. I'll just leave it at that. You could read about it in the book if that's your cup of tea. Okay, thanks for watching.